Hello everyone, welcome back. Last time we were looking at Newton's laws. We looked at Newton's first law of motion, which was the law of inertia. We looked at Newton's second law of motion, F equals ma, and we looked at Newton's third law of motion, the action-reaction law. What we're going to do today is start taking a look, or continue to look, at some more forces that we could use in Newton's laws, forces that will affect the motions of different objects, and see what kind of characteristics these forces have and how we can use them and do some calculations with them. One of the most common forces that we experience all the time, really all the time, is the force of gravity. The Earth pulling us down, causing this force acting on us. This was not a well understood force until Isaac Newton developed what we now call the Newton's law of universal gravitation. That's what we're going to take a look at right now. First of all, why is it referred to as the universal gravitation? What do we mean universal? Prior to Isaac Newton, somewhat prior to him, quite a bit prior, it was not really understood that there was a single set of laws that would govern things in the sky, in the heavens, what would we call the celestial realm, in addition to what was happening here on Earth, what we would refer to as the terrestrial realm. So it was thought that there was one law of motions that described motions in the heavens, in the celestial realm, the motions of the planets and the sun and the moon, and a different set of laws that govern motions here on the Earth, in the terrestrial realm. What Isaac Newton showed was that this particular law in particular, the law of universal gravitation, worked in both realms, the celestial and the terrestrial. There was a single law for the universe, this law of gravitation. So what did it state? Well, the idea is that for any two objects in the universe, any two physical bodies, for example, an apple and an orange, any two objects, anything you want to pick out, let's say, and I'll stick some numbers in with these in just a second. For any two objects in the universe, let's imagine that these two things have a mass. The first one has a mass of m1, the second one has a mass of m2, and let's imagine that the distance between them is r. So r is the distance between them. Now let's be a little bit careful. When we say the distance between them, what do we mean? Do we mean the distance from the closest point, from this edge to this edge, or what do we mean? Well, to be precise, well, a little bit more precise, we mean from center to center, from the center of one object to the center of the other object. What do we mean by the center? What's the center of some oddly shaped object like this calculator? I mean, where's the center? Well, we'll leave that just for the time being. Just imagine that somehow you can define where the center of an object is. Then, the distance r is measured from the center of m1 to the center of m2. What Newton's law of universal gravitation states is, then, that m1 creates an attractive force on m2. In other words, m1 pulls m2 toward it. This is an example of a field force, not a contact force. These do not have to be physically touching each other. m1 pulls on m2 toward it. So there's going to be a force acting on m2 toward m1. We'll call that, how did we refer to these forces last time? We'll call this one F21, and that's a vector. So the force on object 2 caused by or from object 1. Likewise, m2 attracts m1, creates an attractive force on m1. So m1 is pulled toward m1. We'll call this one F12. The magnitudes of these forces are equal to each other. F12 equals F21. And this universal law of gravitation likewise obeys Newton's third law of motion, so that these two are equal and opposite. So these forces in particular, this gravitational attraction due to Newton's law of universal gravitation, certainly follows Newton's third law of motion. Now, what is the magnitude of these forces? They're the same magnitude, so what is the magnitude of the force? Well, what Newton said was that the force is proportional to m1. Now, I'm going to use this little symbol. Sometimes it's written kind of like this, kind of like an alpha or something like that. Typically, when I write it, I'll just write it as a circle and then a semicircle. This just means proportional to. So the force is proportional to m1. What does that mean? That means if we double m1, we make it twice as big, the force of attraction is twice as large. In other words, if m1 is twice as big, m2 is attracted toward it with 2 times the force. Likewise, m1 is attracted to m2 with 2 times the force. So doubling m1 changes the amount of attraction that m2 has for m1, but also the attraction that m1 has for m2. You might then imagine, likewise, if it's proportional to m1, it's also proportional to m2. So likewise, if we triple m2, we triple the amount of force, and we triple the force acting on both of them. It also depends on the distance. The larger the distance, the smaller the force. But it doesn't decrease as just 1 over r, it decreases as 1 over r squared. So the force is actually proportional to 1 over r squared. We call that an inverse square relationship. Inverse square of the distance, so 1 over r squared. Now it turns out that there is also a constant of proportionality that we have to stick in there. So we can write this actually as an equality. F equals m1 times m2 divided by r squared, and the constant of proportionality we write as a capital letter G. Oddly enough, this constant is referred to as big G. So when we talk about big G, we mean this constant that actually comes into Newton's universal law of gravitation. The law of universal gravitation, or sometimes the universal law of gravitation, either one is the same thing. The value of G is 6.67 times 10 to the minus 11th. And then to make the units work out right, we'll put G in terms of the standard SI units. In order to get units of newtons on the left side, after multiplying by 2 units of kilograms on the right side and dividing by a unit of meters squared, it turns out that the units of big G are Newton meters squared per kilogram squared. There we go. Now, let's notice this number, 6.67 times 10 to the minus 11. Remembering what we've already talked about in terms of numbers, tell me something about that number. What is it? It's very, very small. Big G is a very, very small number. If we were going to write this out, not in scientific notation, it would be 0. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 6, 6, 7. So 0.000000000000667. I think I've got that right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep, that's it. That is a very small number. Well, what does that mean? Well, let's stick some numbers in here and find out. Let's find out what that means. Let's imagine that we have an apple with a mass of 120 grams and an orange with a mass of, let's say, 480 grams. And that's actually pretty close to what these are. I just massed them. And let's put them at a distance of, let's say, half a meter apart. So 50 centimeters. From center to center, 50 centimeters. Well, Newton's law of gravitation tells us that there's actually a force of attraction between them. The apple attracts the orange attracts the apple. Let's figure out what's the strength of that force. Well, we have that F is equal to G m1 m2 over r squared. Let's say m1 is 120 grams, m2 480 grams, r 50 centimeters. So we have 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. That's big G, times m1. Well, let's put this in terms of kilograms. 120 grams would be 0.120 kilograms times M2, 480 grams, that is 0.480 kilograms, divided by R, 50 centimeters, let's write that in terms of meters, so that would be 0.500 meters squared, R squared. Divide that out, let's notice the units, we've got kilograms times kilograms and a kilogram squared in the denominator, they cancel. We have meters squared and a meter squared in the numerator, they cancel, and we end up with units of newtons, which is what we would hope for in terms of a force. Multiplying them out, what do we get? 1.54 times 10 to the minus 11th newtons. And again, notice, what does this tell us? 10 to the minus 11? That is a very, very small number, a very, very small force. If I were going to write this out not in scientific notation, this would be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 1, 5, 4 newtons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. 0.0000000000154 newtons. It turns out that that's the weight, how much something would weigh if it had a mass of 1.57 nanograms. In other words, billionths of a gram. A gram is about, say, the mass of a paper clip or so, something like that. Well, take a billionth of a piece of a paper clip, that would be the weight. The weight of that thing is the actual force of attraction between these two things. What does that mean? That means it's a very, very small force. Are you going to notice that force of attraction? Typically, you're eating an apple and you feel the apple attracted to an orange nearby. No, this force is extremely small and it's not something you would ever typically notice in your ordinary everyday life. The force is strong enough to be measured in a very, very precise experiment that's done in a laboratory. If these objects had large enough mass so that the force was actually strong enough to be measured by a very, very accurate measuring device. But this sort of force is not the sort of thing that you would ever notice in your ordinary everyday life between two ordinary objects that you're dealing with. So when would we experience this kind of force? When does gravity become something that we can measure? Well, to make this number large enough, typically one of these things has to be very, very big. M1 has to be very, very large, or M2 has to be very, very large in order to make a force that is actually a measurable or noticeable quantity. How big does M have to be? What about the mass of the Earth? What if we were to put the mass of the Earth in there for one of these objects? What kind of force would we experience in that case? Well, let's try it. Let's stick that in and see what happens. Let's imagine then that we've got the Earth here and then some object, whatever that object is. Maybe we want to talk about this orange or something like that. So we've got this other object, the orange. Keep in mind, this is completely not to scale, obviously. I mean, the Earth is huge, and then we've got some other object, some distance above the surface of the Earth. The mass of the Earth, and I'm going to use a very, very old astronomical symbol for the Earth, just when we're putting things in equations and things like that, just to remind us that certain quantities pertain to the Earth. And that is a circle with a little plus sign in it. It's just a very old astronomical symbol, so I'm going to use that to represent the Earth. The mass of the Earth is then, and I'm going to write this as m, with a little subscript of that little symbol for the Earth. So this is mass of the Earth, 5.98 times 10 to the 24th kilograms. Now you'll notice 10 to the 24, what does that tell us? That tells us this is a very, very large number. The mass of the Earth is very, very big, obviously. That then will give us a much, much larger force than the kind of forces, or the force that we were talking about before, between the apple and the orange. Putting a very, very large mass in there means we're going to get a much larger force, in general, obviously. The distance between them, the mass of the object, I'm just going to leave that as arbitrary. I'll just leave that as m, and we'll see how that works out in the equation. So mass of the Earth and mass of the object, m. What's the distance between them? Remember, r is the distance from center to center. So r will be measured from the center of the Earth to the center of the object. That's r. I'm going to break that down into two parts. Let's imagine that our object is some distance h above the ground level. So the distance r we can break up into the two parts, the distance from the center of the Earth to the surface of the Earth, to the ground level, and then from the ground level to the object itself. That distance that the object is above the surface of the Earth, we'll call that h. What's the distance from the center of the Earth to the surface of the Earth? Well, that's the radius of the Earth. Capital R sub Earth, so radius of the Earth. Little r is then the radius of the Earth plus h. Remember, h, whatever the distance is above the surface of the Earth. The radius of the Earth is about 6.38 times 10 to the 6th meters. What is the sum of these two things? 6.38 times 10 to the 8th meters plus h. Remember, how do we go about adding numbers? Using the appropriate number of significant figures. This radius of the Earth has how many sig figs? 6.38, 3 sig figs. Let's imagine we want to add these two things. I'm going to write out this radius in standard form, not scientific notation, just for a minute. So we've got 6, 3, 8. That's 1, 2 places, and I need to move it 4 more. 1, 2, 3, 4. So what is this? 6,380,000 meters. Now let's imagine we want to add h to it. What if h is 1 meter? So let's say we want to add 1. What do we get in that case? Well, this 0 is not significant. What is 0? What is 1 plus a number that we don't know? We don't know what that digit is. I've written it as a 0 now, but remember in scientific notation, we don't know what that digit is. So we really could only write it as a 0. 0, 0, 0, 8, 3, 6. In other words, 6.38 times 10 to the 6th meters. In other words, adding 1 to this doesn't change the value significantly enough that we would actually change the way we write it. Obviously, the distance is larger, but to 3 significant figures, we would not change the way we write the distance. It would still be written as 6.38 times 10 to the 6th meters. The distance is the same to 3 sig figs. Well, what if we were to make this a 2, or a 3, or a 4, or a 5, or a 9? No difference. What if we were to write plus 10 meters? Still, no difference. What about 100 meters? Still, no difference. What about 1,000 meters? Still, no difference. 2,000 meters? No difference. 3,000, 4,000 meters? Still, no difference. What if we were to put 5,000 meters? In that case, we might make an argument that although we don't know what that digit is, we do know it's a 5 or larger, we might round that up to 6.39 times 10 to the 6th. The bottom line is that we could actually have a value for h all the way up to 4,999 and still not change the way we would write this value to 3 significant figures. That's telling us that we can assume that our orange is anywhere from the surface of the Earth to a height of almost 5,000 meters. In other words, 5 kilometers. And we don't need to change the value that we stick in for r. If we want to put this further than that, further than 5,000 meters, or you could also make the argument if you wanted to dig a hole and make h actually less than 0, so you're moving this closer to the center of the Earth, you could go down into a hole that's 4,999 meters or almost 5 kilometers deep and still not change the value of the distance between them. So let's just keep that in mind. When we're talking about the distance between the mass m and the Earth, as long as we keep the mass within almost 5 kilometers of the surface, we can assume the distance between them is just the radius of the Earth. Excellent. So let's stick that in there for r. We're going to assume that we're just going to ignore h, and we're just going to let that the distance between the two equals the radius of the Earth. So let's stick those numbers in and see what we actually get for our force.